What is a probability?
Consider the following situation. There is a basket full of balls. These balls can be yellow, red, blue, or green. Assume that Bernard is picking balls randomly from the basket. Each time he picks a ball of a certain color, he then adds a cross on the board next to the right color. After having done so, he puts the ball back into the basket and gives it a good mix. After a while, one can get an idea of how the different colors are represented in the basket, that is, their proportions. These four proportions for the four different colors can be interpreted as the probabilities of getting each respective color. This is a frequentist interpretation of probability. Often, one uses probabilities to help people make decisions in the presence of uncertainty. For instance, Andres, the ice cream maker, will consider the probabilities associated with good or bad weather in the next few days when deciding how much ice cream to produce. Katja will consider the probabilities of her house flooding, burning, or being damaged by a storm when deciding on her building insurance. Kevin will consider the probabilities of having a traffic jam on the motorway when deciding how to drive to work. What is a probability function? When building a probability model, we map possible outcomes with probabilities, just as we did with the colored balls. In this situation, the possible outcomes were yellow, red, blue, or green. The probabilities of getting the colors could be compared by counting how many crosses have been drawn by Bernard. Of course, we hope that the probability function represents the true proportions, or probabilities, rather than random proportions from a random draw. In our example, one could actually count all the balls in the basket and work out the true proportions, but, more often than not, such an easy and certain determination of probabilities is not possible. Nevertheless, let us assume here that we know what the probabilities are. Normally, if one has a complete probability model, the combined probability of all outcomes is 1, or 100%. In the example, we had 4 colors, and the sum of the probabilities of getting all 4 colors had to be 1. Furthermore, something can happen, or not, but it cannot unhappen. Mathematically, this means that probabilities can only take values between 0 and 1. They cannot be negative. Then, defining a probability function boils down to apportioning or distributing what we call a probability mass of 1 unit between all possible outcomes. The result is what we call a distribution, quite intuitively. Look at that mass of 1 kilogram. Actually, let us consider 1 kilogram of Play-Doh instead. This will be easier to cut and distribute. So, this kilogram of dough is our probability mass, and to create a distribution of probability, we need to cut and distribute this dough between all 4 colors. Looking at the number of crosses, let us assume that the probability of picking a yellow bowl is 25%, so that we must cut 25% of the Play-Doh and allocate it to the yellow color. Similarly, probabilities for red, blue, and green are 15%, 35%, and 25% respectively. In our example, we had 4 distinct possible outcomes. This is not always the case. We must now distinguish between discrete and continuous outcomes. Discrete outcomes are distinct. For instance, if Jonathan throws a die on the floor, the outcome is either 1, 2, 3, 4, 5, or 6. Once the die stops, the outcome is clear and is 1 and only one of those outcomes. The number of discrete outcomes does not need to be finite, but it must be countable. For instance, the number of raindrops falling on a roof in a given year is a discrete random variable, which can be very large and does not have any obvious maximum. On the other hand, a continuous outcome can only be expressed as a range. This often causes confusion. For instance, the distance at which Jonathan threw the die is a continuous random variable. In this case, it seems that the die stopped at 2 meters and 12 centimeters. This looks like a discrete outcome, but in fact it is not. Let's zoom in. Now, let us move the die by 1/100th of a centimeter away from Jonathan. Now, let's zoom back out. Do you see any difference? No, there is no apparent difference, because we were considering a distance of either 211, 212, or 213 centimeters. But there is an infinity of outcomes that would end up being considered 212 centimeters. It suffices to zoom in close enough to find more intermediate outcomes. Hence, 212 centimeters, really, is a range of 211.5 to 212.5 centimeters. And within that range, there is an infinity of possible outcomes. To summarize, continuous outcomes are expressed as a range only, and consequently, there are no distinct outcomes, such as 1, 2, 3, 4, 5, or 6 when throwing a die. Now that the difference between discrete and continuous outcomes has been made clear, let us focus back on the distribution of probability mass between outcomes. The way the mass, our Play-Doh, is apportioned is different for discrete or continuous random variables. For discrete distributions, bits of Play-Doh are distributed over the possible distinct outcomes. The result is what we call a probability mass function, PMF in short. For continuous distributions, the mass is spread over the range of possible outcomes. The Play-Doh is spread or rolled out into the desired shape. Note that the thickness of the dough should be uniform, such that the height of it at any given point is proportional to the likelihood of an outcome in that region of outcomes. The function corresponding to the shape or the height of that dough is what we call a probability density function, or PDF in short. Importantly, this height is a density, not a probability. A probability must still be a mass, even in presence of continuous outcomes. Therefore, one must cut a slice off the dough and weigh it to work out the probability associated to the range corresponding to the slice that was cut. In this example, the probability of an outcome is 15%.